bondings are only two types. They are ionic and covalent bonds. But today's topic is intermediate bonding, which means in between ionic and covalent bondings. And we'd get substances having both ionic properties and covalent properties because they would have both type of bonding. So this we call intermediate bonding. In the previous topic, when we were studying covalent substances, we got some covalent substances are 100% covalent, not having any ionic character. But when you will study ionic compound, you will not get this. None of the ionic compounds is 100% ionic, which means the all ionic compounds will have a small or big degree of covalency. They must have this. And how you get this? The differences between ionic compounds and covalent compounds are studied using electron density map. This is X-ray diffraction method. That the maps show clear difference between ionic bonds and covalent bonds. If that is ionic bond, you would get the ions are clearly separate. Okay, they're not overlapped. But if they're covalent substance, suppose here hydrogen chloride, then in the middle, look at the middle, they are overlapped. In X-ray diffraction method, you would get the electron density map like they're together is one. They're joined, they're connected. Okay, so this is the big difference between ionic and covalent substances. So now I'm going to show how an ionic compound gains covalency. So with an example of sodium chloride. Okay, there are actually many, but I'm just drawing two: sodium ion and chloride ion. The ionic bond is the attraction between cation and anion. This is right, but specifically, the nucleus attracts the electrons of the anions. Okay, this is ionic bond specifically. You may have the question: why not the opposite? Why the nucleus of the anion are not supposed to attract the electrons of the cation? Because cations, the nucleus of cations is more powerful than nucleus of the anions. Why? Because when this was an atom, then this had equal number of protons and electrons. And when this has lost electron, then the cation has less electron than its proton. What does it mean? In the ratio of proton and electron, you get more proton than electrons. So protons are here more. So nuclear charge now is stronger. So its nucleus are holding the electrons, all the electrons, but this is still more powerful because this has one more proton than its electron number. So this is how its nucleus can attract the outer negative things, which are the electrons of the anions. Here you get electrons of the chloride. And this doesn't happen for nucleus of the anion because when this was an atom, then this had equal number of proton and electrons. Means charges were equal. When this gains an electrons, anion forms by gaining electrons. Then this electron number is greater than proton number. What does it mean? The nucleus has been weaker than its atom because this is now tired of holding more electrons. So this is how the nucleus is less powerful than nucleus of the cation. So what you get, the nucleus of cation will attract the electrons of the anions, and that would be the bond. And when you think that this is the bond, then should the nucleus of the cation distort the electrons of the anion? When the nucleus of the cation will pull out the electrons of the anions, and the thing will happen that the electrons of the anion will move towards the cation. This we call distortion of the electrons of the anion. And electron density between the particle will increase, right? When electron density between two particles increase, this we call covalency. Because initially I told that when you get a covalent bond, then they're connected, they're overlapped, and in the overlapping you get greater electron density between them. But when they're ionic, then they should be separate, individual. They all are individual, not overlapped. And the charges that's supposed to be sodium is +1 and chloride is -1, they will also be slightly changed, because when the sodium is +1, because it has lost one electron, but it's again gaining some electron density towards it, so this will be less positive than +1. And for -1, when this has gained an electron and having -1, but if electron density around chloride moves away from chloride, then it would be less negative. Okay, less negative. So that you would get that develops covalency, or that reduces ionic character. If I compare this compound with another compound, this is here you see again sodium, but this time I'm giving you here, instead of chloride, I'm giving here bromide. Bromide is bigger than chloride, so that you get here bromide. And how would happen? How would the same thing happen here? And here you got that this develops covalency, and for sodium bromide this would also develop covalency. And which of the compounds will have greater degree of covalency, sodium chloride or sodium bromide, do you think? Here sodium attracting the electrons of chloride, and here the sodium attracting the electrons of bromide. The sodium is same, and its attractive power, sodium's attractive power is same in both the compounds, but instead of chloride you get here bromide. Bromide is much bigger than chloride, and when bromide is bigger, then the electrons are away from its nucleus because it's big in size, so the electron would be distorted more by the sodium ions, so which means that there will be greater distortion. Now I show you another example. Here I'm changing the cation. In these two compounds you got the cation are same, sodium and sodium, but anions were different. But I now show you different cation. Here you see another example. This is I'm giving you magnesium, okay, and I give here chloride, same. This was chloride and this is still chloride. Okay. So now compare these two compounds. Now this was sodium chloride, now this is magnesium chloride. Okay, so the size and charges of these two chlorides are same, nuclear charge, everything the same, but instead of sodium you are getting now magnesium. So now what do you think would happen? Here the magnesium will have greater ability, greater power to distort the electrons. Why is so? Because magnesium, look at the charge of magnesium, okay, charge is greater. When charge of magnesium is greater, then this would have stronger power to distort the electrons of the chloride. So here you get this getting distorted and moves towards the magnesium ion, and this would have greater covalency than we are comparing with this compound. Now again, first look at the sodium chloride and sodium bromide. Sodium bromide would have greater covalency. This would have greater distortion or polarization. Why so? Because big anion. When you get big anion, that would have greater polarizability. This property of being polarized, and the tendency of being polarized we call polarizability. What do you call this? Polarizability. So when the anion is bigger, so what we call the polarizability is greater. So which one has greater polarizability? Chloride and bromide? Bromide, because bromide is big. So there would be greater distortion. And compare with sodium chloride, magnesium chloride again will have greater covalency. Why so? Here the chloride are same, but here you get the magnesium. Instead of sodium you are getting here magnesium, and magnesium will have normally greater charge, and magnesium will attract or distort or polarize the chloride more than sodium. This ability of the cation we call polarizing power. Okay, so you are getting two terms to explain these facts. One is the property of cation which polarize, we call this polarizing power, and another property we call of the anion, what do you call this? Polarizability of anion. And you already got this. Polarizability depends on just size. When you get big anion, then it's easier to be distorted. So polarizability of the bigger anion is greater than the smaller anion. If you get here iodide, that would have even bigger in size. big size, and that would have greater polarizability, and covalency would be greater in the compound. And for cations, what do you get? If the cations have greater charge, then what would happen? That would have greater polarizing power. And compare here sodium with magnesium, you get sodium is +1, magnesium is +2. So magnesium would have stronger polarizing power. And polarizing power not only depends on the charge, this also depends on size. How is that? If you get two cations, suppose here calcium and magnesium, if another is calcium, both of them have same charges, but magnesium is smaller than calcium, then certainly magnesium would have greater polarizing power than calcium. So polarizing power, this belongs to cation again, and this depends on two things. One is its charge, greater the charge, greater the polarizing power. What is the other thing? This is size. Smaller the size, greater the polarizing power. And these two terms, we said, these two conditions together, charge and size, if we apply these two together, we derive a new term, what is called that charge density, which means charge divide size. Charge density of cations depends on charge, and if you think that this is proportional, then greater the charge, greater the charge density. And here you get size. If size is bigger, then charge density will be lower. And charge density is the factor. Magnesium and calcium have same charge, but charge density of magnesium is greater. Why? Because this is smaller. The small charge same for both the ion charge same, but size different. Ability to distort, this polarizing power would be greater than calcium. And if we apply this concept in the periodic table, in the periodic table we have the atoms. But when you think about polarizing power or polarizability, you should consider them to be ions and not the atoms. Suppose you get here group 2 elements. So look, what would happen to their polarizing power down the group? In a group, charges are same and size increases, because in every step you would have more shell. Charge density would decrease, and when their charge density will decrease down the group, then they will be less polarizing, so polarizing power will decrease. And accordingly, if you get the compound, suppose here you get beryllium chloride and you get here magnesium chloride, then suggest me which one is more covalent. You see chloride is same in both the compound, but the difference in beryllium and magnesium. Look here, beryllium and magnesium have same charge, but because beryllium is a smaller ion, so charge density of beryllium will be greater, so that would have greater polarizing power. So polarizing power decreases down the group. So when this is more polarizing, so here in this compound beryllium chloride, beryllium will polarize the chloride more than magnesium polarize the chloride. This is how you will get that beryllium chloride will be more covalent and magnesium chloride will be more ionic. So compounds down the group will have more ionic properties and less covalent. If you think what would happen across the period, then I give some ions again. So what do you think? How do they vary? Here you get sodium and magnesium. Certainly charges are increasing from left to right side in a period. Charges are increasing and their size are decreasing. So what would be their charge density? Which is charge density will increase. Their polarizing power will increase. So from sodium to magnesium and magnesium to aluminum, the polarizing power will increase. Now think about this sodium. If sodium bonds with chlorine, this is sodium chloride. And if magnesium bonds with chlorine, this is magnesium chloride. Which one do you think is more covalent? Sodium chloride or magnesium chloride? This should be magnesium chloride, because chlorides are same, so things doesn't depend on chloride. The difference is here sodium, here is magnesium, and magnesium has greater charge and greater charge density. So when magnesium has greater charge density, then that you would say that this would have greater polarizing power. So this would distort the electron of chloride more than that can be done by sodium ion. So this would have greater covalency and less ionic properties. So across the period, when you go left to right, gradually you will get the next compound will be totally